So now we've had an introduction to quadratic extensions of rings, particularly quadratic extensions of the integers, and the one special case that we like to play with a lot is the Gaussian integers. So we want to take this a step further and see what does that structure, specifically the norm function on a quadratic extension, what is that going to tell us about whether or not an element in one of these quadratic extensions may be factored? So the goal of this video is to explore that question by looking both at the Gaussian integers and also at a couple other quadratic extension fields and see how does the norm give us information about factorability. And most important definition in this video is what it means for an element in a ring to be irreducible. So first of all, let's think about norms and factorizations for a moment. The number one most important property of the norm function on a quadratic extension is that it is a multiplicative function. In other words, the norm of a product is equal to the product of the norms. So for example, in the quadratic extension by I, so the Gaussian integers, negative 8 plus 4i actually factors into 3 plus I times negative 2 plus 2i. And if we take the norms of these three elements we've written down here, the norm in the Gaussian integers of negative 8 plus 4i is the product of negative 8 plus 4i with its conjugate, which is 80. Meanwhile, the norm of 3 plus I is 3 squared plus 1 squared is 10. The norm of negative 2 plus 2i is 8. And sure enough, 80 is equal to 10 times 8. So there's an illustration of this multiplicativity of the norm in the particular example of the Gaussian integers. But of course, it works in any quadratic extension. Let's take the quadratic extension by the square root of 13 of the integers. So the norm in this quadratic extension ring is going to be the product of a plus b squared root of 13 by its own conjugate. So when we simplify that out, what we end up with is a squared minus 13b squared. Again, remember the norm, even though it takes in a funny-looking quadratic number as its input, it will always output an element of the base ring, which in this example is the integers. So a squared minus 13b squared, that's going to be a nice friendly integer. So negative 20 minus 4 radical 13 happens to factor in this ring into a product of 1 minus radical 13 and 6 plus 2 radical 13. And if we compute the norms of these three elements, the norm of negative 20 minus 4 radical 13 turns out to be 192. The norm of 1 minus the square root of 13 turns out to be negative 12. By the way, this is one important difference between an arithmetic norm and a geometric or a topological norm. In geometry and topology, norms always refer to non-negative functions. But in the case of an arithmetic norm, we can have a negative value, as we do here, negative 12. Meanwhile, the norm of 6 plus 2 radical 13, work that out, it's negative 16, and sure enough, negative 12 times negative 16 is 192. So what the norm is really good at doing is reducing a question about multiplicativity in a complicated ring, namely a quadratic extension ring, and reducing that to a question about multiplicativity of plain vanilla integers, and that just happens to be something that we know a lot about. So here's a question. If I want to decide whether or not 5 plus 2 square root of 5 factors in the quadratic extension z radical 5, then one idea might be to check the norm. Let's take 5 plus 2 radical 5 and look at its norm. Its norm is the product of itself with its conjugate, which once we've worked that all out, we find out that the norm of this element is equal to 5. Now, if this number happens to factor into a times b, then by taking the norm of both sides, and then observing that the norm is a multiplicative function, so the norm of a times b is the norm of a times the norm of b, we find out that if this number factors into a times b, then the products of the norms of a and b has to be 5. But 5 is a prime integer. So now we're using a fact about the integer 5 as opposed to a fact about the complicated quadratic number 5 plus 2 radical 5. And so we can conclude that either the norm of a or the norm of b has to be 1 or negative 1. In order that their norms multiply together in the ring of integers to give me 5, because 5 is a prime integer. But remember, having a norm of plus or minus 1 is going to imply that in our original ring, a or b has to be a unit. So does 5 plus 2 radical 5 factor? Well, it might, but if it does, then one of those factors has got to be invertible. It's got to be a unit, which is actually not very interesting in the grand scheme of things. So if this number factors, it doesn't do so in a fashion that's very interesting. So here's the important definition. An element of a ring is called irreducible if it cannot be written as a product of two elements in that ring unless one of those elements happens to be a unit. So I can't break apart an irreducible element of a ring into two pieces unless one of those pieces is a boring old unit. For example, in the polynomial ring over the rational numbers, the polynomial 18 minus 12t has a factorization, and yet we're still going to say it's irreducible. How come? Well, a freshman algebra student can tell you that 18 minus 12t has a common factor of 6 that we can pull out, so it's equal to 6 times 3 minus 2t. But it turns out this is really the only way to factor p in any meaningful sense, and one of those factors, 6, happens to be a unit in the polynomial ring over the rationals, because it's also a unit in the polynomial in the ring of rationals itself, the field of rational numbers. So since one of those factors is a unit, this factorization doesn't count. Note, however, that this factorization would count over the integers, because 6 is not a unit in the ring of integers. So there's some subtle connection and maybe a relationship between factorability over the integers and factorability over the rational numbers. File this away, because in our next class we're going to talk about Gauss's lemma, and Gauss's lemma spells out specifically the relationship between factorability over the integers and factorability over the rational numbers. So put that on a shelf and just make the observation here that even though p doesn't factor in a meaningful sense over the rationals, it does factor in a sense that's meaningful over the integers. And here's a point where I have to caution you very strongly, that we just saw what the definition is of irreducibility. And it looks an awful lot like the definition that you might get in number theory for primality. Is there a difference between a number being irreducible and a number being prime? And the answer is yes. These are not the same thing in general. We haven't actually seen a more general definition of what it means to be prime. But in order to define what it means to be prime, we actually use a little bit more ring theory and define what it means for an ideal to be prime. And a number then is prime if the ideal that it generates is a prime ideal. It turns out that there's a subtle difference between primality and irreducibility. It's a difference that really isn't a difference in the integers or in a lot of the friendly rings that we work with, but there are examples of rings out there in which primality and irreducibility are not the same thing. So just a word of caution for now that irreducible does not always mean the same thing as prime, although it will in the friendly rings that we happen to be looking at today. All right. So let's look at the example of the Gaussian integers again and start with an observation. That because of the multiplicativity of a norm function, if I'm able to factor a reducible number in one of these rings, then each of the factors that it factors into has to have a norm that's smaller than the norm that I started with. So factoring is going to reduce the norm of a reducible number, hence the word reducible here. So let's think of an example. How about 3 plus 4i? And I want to ask the question, can we factor 3 plus 4i over the Gaussian integers? In the same way as we did a few slides ago, let's begin by asking the question, what is its norm? So we'll compute the norm of 3 plus 4i. The norm is 25. And if we look at the set of all Gaussian integers that have a norm equal to 25, that looks like this circle of radius 5 in the complex plane. So it includes 3 plus 4i, but also 4 plus 3i, negative 3 plus 4i, and so on. So it includes a lot of other things. And according to this observation, if 3 plus 4i factors, then that factor, both of the factors, say, are going to have a smaller norm. So they must come from inside of this circle. The only factorization, in fact, that counts because of the multiplicativity of the norm function, the only factorization that will show that 3 plus 4i is not irreducible is a factorization where none of those factors have a norm of plus or minus 1. So the only factorization we're going to be interested in to show 3 plus 4i is in fact reducible is going to be the factorization of the integer 25 into 5 times 5, or potentially negative 5 times negative 5. So this is the only factorization that's going to give us a factorization that counts. So what we're going to do now is look for factors that have a norm equal to 5. In other words, in the Gaussian integers, these are going to be those Gaussian integers that lie on the circle a squared plus b squared is equal to 5, so a circle of radius radical 5 in the complex plane. It turns out there are 8 of those. Here they all are. There are 8 possibilities. So that already has reduced our universe of possible factors to a very small universe. We only have 8 numbers that are possible to work with. From there, we could just employ a process of guessing and checking. But if we want to be a little bit more geometric about it, what we might do is take one of these candidates, like 2 plus I, and ask, is there another one of the candidates from among these 8 possibilities that I can multiply 2 plus I by and get 3 plus 4i? We'll take a look at the angle that 2 plus I makes with the x-axis, and just imagine doubling that angle. So just going up by another angle of theta here. Then, if I were to multiply 2 plus I by itself, then that product would have an angle that is twice the original angle of 2 plus I, and it just so happens that that angle exactly hits 3 plus 4i on the bigger circle here. So we might make an educated guess that if I multiply 2 plus I by itself, that I get 3 plus 4i. and you should check for yourself that that is indeed the case. So knowing the norm of 3 plus 4i, 25, factors into 5 times 5 actually helped us to reduce our search for what factors among the Gaussian integers might actually multiply together to give me 3 plus 4i. So the norm function is your best friend in the study of factorability. And we're going to see later on that similar considerations will help us decide whether a polynomial is factorable. And in our next series of videos, we're going to look at the question of polynomial factorability in some more depth and talk about Gauss's lemma and Eisenstein's criterion. That's where we're going with this next.